Welcome to our channel. Today, we're diving into the fascinating world of black holes, those cosmic enigmas that have captivated scientists and stargazers alike for decades. From the smallest to the most massive, we'll explore the different types of black holes and what makes each one unique. We'll journey to the hearts of dying stars, the centers of galaxies, and even back to the very beginning of the universe itself. So, buckle up, space cadets, as we embark on an exhilarating cosmic adventure to unravel the mysteries of these gravitational behemoths. Get ready to have your mind blown wide open. Let's kick things off with the most common type of black hole, stellar black holes. Now, these cosmic heavyweights are born from the death throes of massive stars far more massive than our own sun. Imagine a star, say, 10 times the mass of our sun, running out of its nuclear fuel. Without the outward pressure from nuclear fusion to counterbalance the relentless inward pull of gravity, the star's core collapses in on itself. This collapse is a runaway train wreck on a cosmic scale. The core implodes, reaching unimaginable densities, and boom, a supernova erupts, blasting the star's outer layers into space in a spectacular display of celestial fireworks. What's left behind? A region of space-time so warped, so dense, that nothing, not even light, can escape its gravitational clutches. That, my friends, is a stellar black hole. Now you might be wondering, how big are these stellar black holes? Well, they're not exactly pocket-sized, but they're not galactic monsters either. Imagine squeezing all the mass of 3 suns into a space the size of a city. That's the kind of density we're talking about here. And that, my friends, is a stellar black hole in a nutshell, a cosmic graveyard for massive stars. But don't let their size fool you. Stellar black holes are incredibly influential objects in the universe. They warp space-time around them, creating gravitational distortions that can affect the orbits of nearby stars and even bend the path of light itself. We can detect these gravitational effects, and that's how we know black holes are out there, lurking in the darkness. It's like their gravitational shadows give them away, even though we can't see them directly. Now, if stellar black holes are the heavyweights, then supermassive black holes are the undisputed champions of the cosmos. These behemoths lurk at the centers of most galaxies, including our very own Milky Way. Talk about a cosmic heavyweight. Supermassive black holes can have masses millions, even billions of times greater than our sun. It's mind-boggling to even fathom that much mass concentrated in one place. But here's the thing, despite their immense size, supermassive black holes are not cosmic vacuum cleaners, randomly sucking up everything in sight. In fact, they play a crucial role in the evolution of galaxies. Think of a supermassive black hole as the conductor of a galactic orchestra. Its immense gravity orchestrates the motions of stars and gas within the galaxy, influencing its structure and evolution over billions of years. Now, how these galactic giants formed is still a bit of a mystery. One theory suggests they formed from the mergers of smaller black holes, like stellar black holes merging over eons. Another theory proposes that they formed directly from the collapse of massive gas clouds in the early universe. It's like the universe skipped the whole star formation process and went straight for the supermassive black hole jackpot. Whatever their origin story, supermassive black holes are some of the most fascinating and enigmatic objects in the universe. They are windows into the extreme physics of gravity, pushing our understanding of the cosmos to its limits. We've talked about the stellar lightweights and the supermassive heavyweights, but what about the middleweights of the black hole family? That's where intermediate black holes come in. These cosmic enigmas bridge the gap between their smaller and larger cousins, with masses ranging from hundreds to tens of thousands of times that of our sun. They're like the missing link in the black hole evolutionary chain. But here's the catch, intermediate black holes are incredibly elusive. They're like the cosmic ninjas of the black hole world, lurking in the shadows and rarely giving us a glimpse of their existence. Why are they so hard to find? Well, for starters, they don't have the same dramatic effects on their surroundings as supermassive black holes. They're not anchoring galaxies or gobbling up stars at a frantic pace. And unlike stellar black holes, which form from the death throes of massive stars, the formation mechanism for intermediate black holes is still shrouded in mystery. It's like the universe is playing a cosmic game of hide-and-seek with us. But don't despair, intrepid explorers of the cosmos. Astronomers are hot on the trail of these elusive entities, using ever more sophisticated telescopes and techniques to track them down. One promising avenue is the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects like black holes merging. By studying these cosmic tremors, we can glean clues about the masses and properties of the black holes involved, potentially revealing the presence of intermediate black holes. Another strategy is to search for the telltale signs of their activity. While they may not be as ravenous as their supermassive counterparts, intermediate black holes can still accrete matter, heating up the surrounding gas and emitting X-rays. Now, let's journey back in time to the very beginning of the universe, just fractions of a second after the Big Bang, when the cosmos was a hot, dense soup of primordial particles. It was during this chaotic era that a special breed of black hole, known as primordial black holes, may have formed. Imagine the early universe, a chaotic sea of energy and matter, where fluctuations in density could create pockets of space-time so dense that they collapsed into black holes. That's the essence of primordial black holes. Unlike their stellar and supermassive counterparts, which form from the collapse of stars or gas clouds, primordial black holes are thought to have emerged directly from the fabric of space-time itself, like wrinkles in the cosmic tapestry. Now here's where things get really interesting. Primordial black holes could span a vast range of masses, from minuscule specks smaller than an atom to behemoths rivaling the mass of a mountain. The smaller ones, known as micro black holes, would have evaporated by now due to a quantum mechanical process called Hawking radiation. But the larger ones could still be lurking out there, remnants of the universe's infancy. But here's the catch. Primordial black holes are still theoretical. We haven't definitively detected one yet. They're like cosmic ghosts, their existence hinted at by our understanding of the early universe, but yet to be confirmed by direct observation. However, their potential implications are profound. Primordial black holes could account for a portion of the universe's dark matter, the invisible stuff that makes up the majority of its mass. They could also play a role in the formation of larger structures in the universe, acting as seeds around which galaxies and clusters of galaxies coalesced. It's like the universe planted these cosmic seeds billions of years ago, and they've been growing ever since. Now let's shrink our perspective and dive into the realm of the incredibly small, where the laws of physics as we know them start to break down. We're talking about micro black holes, tiny black holes that could theoretically exist at the subatomic level. Imagine a black hole smaller than an atom, a singularity in space-time so tiny that it makes a proton look like a giant. That's the mind-boggling scale we're dealing with here. Now you might think that something so small would be insignificant, but micro black holes could hold the key to unlocking some of the biggest mysteries in physics, like the nature of gravity and the unification of quantum mechanics and general relativity. But here's the catch. Creating a micro black hole is no easy feat. It would require concentrating an enormous amount of energy into an incredibly small space, something that's only possible in the most extreme environments in the universe, like the collisions of high-energy particles. Think of the Large Hadron Collider, the world's most powerful particle accelerator, smashing protons together at nearly the speed of light. Some physicists believe that these collisions could create microscopic black holes, albeit for fleeting fractions of a second. Now before you start worrying about a micro black hole swallowing up the Earth, let me reassure you. These tiny black holes would evaporate almost instantly due to Hawking radiation, releasing their energy back into the universe in a burst of particles. But even if they're short-lived, the detection of micro black holes would be a monumental discovery, providing us with a glimpse into the quantum nature of gravity and potentially revolutionizing our understanding of the universe at its most fundamental level. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content. We've journeyed from the hearts of dying stars to the edges of the universe, exploring the mind-bending world of black holes. Let us know in the comments which type of black hole you found most interesting. Until next time, keep your minds open and never stop exploring the wonders of the cosmos.